Hey everyone, and welcome. Sound, it's literally all around us, all the time. But have you ever stopped to think about what it actually is? Well, today we're going to break it all down, from a tiny little vibration all the way up to some seriously cool tech. All right, let's kick things off with a bit of a brain teaser for you. What on earth could a bat possibly have in common with a submarine? I know, it sounds like the start of a bad joke, right? But trust me, the answer is rooted in the physics of sound. And by the end of this, it's all going to make perfect sense. So, to get to the bottom of that puzzle, we've got to go back to square one. I mean, we hear things constantly, but what is sound? Like, really, what's physically happening when a noise hits our ears? Okay, so it all starts with one simple thing, a vibration. Just picture it. You pluck a guitar string. That little wiggle creates a chain reaction. It shoves the air particles right next to it, which then shove the particles next to them, and on it goes. It's basically a massive, invisible game of dominoes, pushing energy out in a wave. All right, so we've got it. Sound is a wave. Simple enough, right? Well, not so fast. It turns out there are different types of waves. And to really get what sound is, we need to figure out exactly which category it falls into. Okay, the first big division is this. Some waves need something to travel through. A medium, like air or water, or even a solid. These are called mechanical waves. And guess what? Sound is a mechanical wave. It needs those particles to play dominoes with. That's the classic reason why, in space, nobody can hear you scream. There's no air, no medium. Light, on the other hand, is totally different. It's an electromagnetic wave. It doesn't need any medium at all, which is a very good thing. Otherwise, we'd be sitting here in the dark with no sun. But wait, there's more. We can get even more specific. Sound is what we call a longitudinal wave. And here's a fantastic little trick to remember the two main types. For transverse waves, the particles wiggle up and down, perpendicular to the direction the wave is going. The mnemonic here is PT-SUR, perpendicular transverse. Think of making waves with a rope. But for longitudinal waves, the particles move back and forth in the same direction as the wave. For this one, remember, sleep later, same longitudinal. Sound is exactly that. It's a push-pull wave, kind of like when you push one end of a slinky. Okay, let's recap. Sound is a longitudinal wave, pushing its way through some kind of medium. Got it. But that doesn't really explain why a deep bass drum sounds completely different from a high-pitched whistle, right? For that, we need to dissect the wave itself. Let's look at its anatomy. First up, we have frequency. This is basically just how fast the vibration is, how many of those back and forth wiggles or oscillations are happening every single second. We measure this in a unit called hertz, which you've probably seen written as Hz. And the second key part is amplitude. So frequency is the speed of the vibration. You can think of amplitude as its power or its intensity. It's all about how much energy is packed into that wave, how big the push is on those particles. A tiny little push means a small amplitude. A huge, powerful shove, that's a big amplitude. So, what does all this mean for our ears? How do frequency and amplitude actually translate into what we hear? Well, it's actually super simple. Frequency controls the pitch of a sound. The higher the frequency, the higher the pitch. Think of a tiny whistle. The lower the frequency, the deeper the pitch, like a big bass drum. And amplitude? That's even easier. It just controls the loudness. More amplitude equals more volume. Simple as that. All right, we know how sound travels through stuff, but what happens when it hits a dead end? Like a wall or a cliff face? Well, it bounces back. This super simple idea is called reflection, and it's responsible for a couple of things you've definitely heard before. Yeah, so this whole reflection thing gives us two effects. The first one is the classic echo, that single, clean copy of a sound you hear when you shout into a canyon. And here's a cool little fact for you. To hear a proper echo, that surface has to be over 17 meters away. Anything closer and you get the second effect, reverberation, or, reverb. That's what's happening when you sing in the shower. It's all those sound waves bouncing off the tiles so fast they just blend together, making you sound like a rock star. Okay, so we've got the basics down pat, but this isn't just some abstract physics lesson. This is where it gets really, really cool. Because once we understood these core ideas, vibration, waves, reflection, we figured out how to use them to create some absolutely incredible technology. The first thing you have to realize is that our ears are, they're kind of limited. The range of sounds we can actually hear is just a small slice of the full pie. A healthy human ear can pick up frequencies from about 20 hertz to 20,000 hertz. Anything below that is called infrasound, and everything above it is ultrasound. We can't hear any of it, but that doesn't mean it's not useful.
In fact, the animal kingdom is full of creatures that live in these hidden soundscapes. Your dog can hear low-frequency infrasound, which might be why some people think they can sense earthquakes coming. And then you have bats. Bats are the absolute champions of ultrasound. They blast out these high-frequency chirps and listen to the echoes to see the world around them in pitch blackness. It's nature's own sonar system.
And that brings us full circle right back to our submarine. It's using the exact same idea as the bat. We just call it sonar, which stands for sound navigation and ranging. The sub sends out a ping of ultrasound. It travels down, bounces off the seafloor, and comes back up. The machine just listens for the echo and times how long it took. And with that one measurement, it can figure out the depth and create a map of a world it can't even see. So there you have it, the answer to our puzzle. What a bat and a submarine have in common is echolocation. They both use sound to see. But this idea of using ultrasound is huge. It goes way beyond just finding the bottom of the ocean. We use its super high frequency vibrations to do amazing things, like gently clean tiny delicate microchips, or find microscopic cracks in bridges before they become a disaster. We even use it in medicine to look inside a person's body. That's what an ultrasound scan is. And even to break up painful kidney stones without any surgery. It's just an unbelievably powerful tool. And it's pretty wild to think that all this incredible technology starts from just a simple vibration, a little tiny wiggle that sends out a wave. And from that, we've figured out how to map the deepest parts of our planet and even heal ourselves. It just goes to show you when we really dig in and understand a fundamental part of our universe, the possibilities are almost endless. It really makes you wonder, doesn't it? What will we hear next?